Today we will analyze key features of quadratic functions in a real-world situation. Real-world situations can be modeled and represented by a quadratic function. The key features are what we focus on, and they have real-world meanings based on the situation. Our example today is dealing with a basketball path, the path of a basketball thrown from the free throw line, which can be modeled by the quadratic function given. F of x equals negative x squared plus 6x plus 7, where the height, which is in feet, of the ball is a function of the horizontal distance feet from the free throw line. So the first two things that it wants us to fill in are what x represents and what f of x represents. Well, in this case, it says that height itself is a function of. This is letting us know that height in feet, the height of the ball, is our output. Our height of the ball is our output, what comes out of this. And the distance tells us what the height is. Going back to the statement, it says height of the ball is a function of the horizontal distance. Hopefully I have enough space. There we go. And this is also in feet. So now we know that our x and our input and our output are, we can look at our table and graph that also show the information for us from the function. Now in this real world situation, starting from the free throw line is when the player has the ball. In this case, it is held 7 feet in the air. This is where the player has the ball as soon as he releases his shot. Then as the ball travels farther away from the free throw line, aka he shot the ball, we put the ball's height in motion. For the people who played basketball, you know that you have to create an arc to increase your chance of making the shot. As we get to 3 feet, we reach a height of 16 feet, and from there, our arc starts returning downwards, where at 7 feet away from the basket, or from the free throw line, we are 0 feet high. The ball lands on the ground. So that is what the information is telling us in the table as well as our graph. You can see on the graph we have a y-intercept, which is where the ball starts from the shooter's hands. It increases all the way to a peak of 16 feet when it is 3 feet away from the free throw line. And then it finally reaches a height of 0 feet when we are 7 feet away from the goal, from the free throw. Now our key features, as I labeled already, our very first one, which is a little hard to see on the graph because it is not on a line. We can find it on our table. Our y-intercept is when our x value is 0. So in this case, that is 0, 7. What this represents is the ball's position. ball's position at the start. You could add more details saying that the ball was 7 feet in the air when the shooter had the ball at the free throw line. Our x-intercept, for the example, for the story that was given, we only have one. It is at the end. It is at the location 7-0. X-intercept being where it crosses the x-axis, which is at 7 feet, the distance from the free throw line. So for our situation, when the ball is 0 feet in height, we're saying the ball is on the ground. And since it is at the end of the trip, we are saying that the ball lands 7 feet away. A little bit more specific, 7 feet away from the free throw line. So in this case, you can kind of word it how you would like, as long as you make a complete thought from the information. Forgot to put a period on that last one. Our vertex in this situation is going to be the max height that the ball was in its path. So in this case, at 3 feet distance from the free throw line, we had a max of 16. 16 feet for the height. What this location means to us is the max height. So if we wanted to answer this question, we would say the max height was 16 feet, 3 feet from the goal. Free throw line, sorry, from the free throw line. One of our last key features is the axis of symmetry. It is where our function would mirror itself at. What point would it start? And that would be at the vertex. Our vertex x value was 3. So our axis of symmetry, the line equation, is x equals 3. Now, what the axis of symmetry means, it doesn't just mean that the function mirrors itself. In our situation, this lets us know this is when the ball starts coming down from its shot. So what the axis of symmetry could mean is the ball, if I can write proper words, the ball starts to come down on its shot path. So in this case, the shooter takes his shot, the ball is increasing, it reaches our axis of symmetry, also our vertex, and then it starts to come down from its shot. Now, when I'm talking about the situation, I'm specifically talking about the story. the basketball starts at 0 distance from the free throw line, and the farthest it goes before it lands is 7 feet. The height, when it lands, it touches the ground, but the highest it goes is 16. There are limits based off of the story that was given. So we need to include that when we're talking about the domain. The domain referring to distance from the free throw line, which is our x. It is bound on both sides. We have a minimum value of 0 where it is on the free throw line, the start of this story. And then it lands 7 feet away. Now, because our range is a little bit different, it does not mean we change anything. This is not our lowest point as it's only 7. Our lowest point is our end point, which goes all the way down to 0. And we already stated that our max is 16 feet. So our range, the height of the ball, can be anywhere between 0 feet, where it is landing, to 16 feet, where it reaches the top of its shot. Now, when we say the function that models the situation, that's referring to the equation itself. It is not asking about the story at all. It simply wants to know the math behind it. So in that case, we're not looking at the boundaries anymore. That would be the same as putting arrows on both ends, allowing us to go through the floor, or even starting past the free throw line. So in this case, if we are saying that this goes on forever in both directions, we have all real numbers for our domain. We're saying that it can be negative values and it can't go past where it hits the ground. Our range still has a max value, but it doesn't have a minimum value anymore. As we can go through the ground, we can keep going into negative territory. So what we say is that our range, our y value, is going to be any value less than or equal to the max height, which was 16. Now, for the people who don't play basketball, don't know how a court is set up, the free throw line normally is 15 feet away from the backboard. So we have to treat this as if it was a shortened basketball court to see if this shooter had a chance of actually making the shot. It states that the free throw line for this shortened basketball court is 6 feet from the basket, that is 8 feet in the air. It wants to know, did the ball make it in the basket? And we need to explain. So, if we look at this, using a different color for our basketball, or for our goal, it says at 6 feet away, the goal is 8 feet into the air. It wants to know, did our shooter make his shot? Now, in order to make it, that means that our pathway would have to line up directly on this point. In this case, you can see that our arc is a little short. It goes below our point, which would mean no, he did not make it. And the reason why, the shot fell short of the goal. So this is just one way you can use the quadratic function and parabolas in a real-world situation. What it looks like whenever we see our y-intercept, in this case was a starting point where the shooter had the ball, Our x-intercept, which is represented as where the ball lands in this situation. Our vertex, which is the max height of the shot, as well as when the ball is finally returning down from its peak height, the axis of symmetry. We can look at the domain and range, figure out how far the ball has traveled, where the ball could have gone in between that shot, and how high or how low the ball went at any given moment. The quadratic function gives us an opportunity to see a lot of different pieces of information all used at once that could benefit us in the long run when we use it.